Hello students, good evening. So in today's session, right, we are going to start with the wave optics. Now, the thing that we are going to cover in this wave optics is because in ray optics we try to focus mostly on the optical phenomena by considering that the light will travel in straight lines. Okay. In wave optics, we will try to mostly look at the wave related phenomena. So here, first we will try to understand what is the theory related to the wave propagation of light, and then we look at the two important phenomena. One is what we call as the interference, and other is the diffraction. Then we'll also talk about some associated phenomena like polarization, etc. Okay, so that is broadly what we have in terms of the wave optics. Now the thing is, in comparison to the ray optics, right, the level of application in wave optics will be little bit limited. Okay, because we'll obviously, when we talk about the interference phenomena, we are going to just look at what is it that we will be able to understand in terms of the interference. Okay, same like mostly we'll talk about here Young's double slit experiment. Then similarly we have for the diffraction we'll have mostly we'll cover the single slit diffraction. Okay, so the purview, right, will be limited to whatever the coverage that we'll have in terms of the syllabus. So with that in mind, right, generally the wave optics part is considered to be little bit more sure in terms of scoring when it comes to competitive examinations, because we are going to, at the end of the day, we'll have a set of formulae that will be coming out of these derivations or these results, and mostly the questions will be limited to those formulae with a little bit of application involved. Okay, so that is the importance. So like if you are looking at any examination, whether it is a NEET or a JEE, we will definitely have questions coming from the ray optics part and wave optics part also. But the advantage with this part is you'll have more surety of getting answers for those questions. Okay, so we'll begin our discussion with this wave optics. So before we go into the wave optics discussion, right, we'll try to understand how the concept of wave phenomena for the light has evolved. Because if you look at the primitive understanding of the light is with the phenomena of what we call as the particle theory or the corpuscular theory. That is what is the primitive understanding of the propagation of light. But the wave theory deals with the propagation of light to be in the form of wave. But this understanding also changed over a period of time. Okay, we will see how the understanding of the wave nature of light itself has changed. But generally, to think about the wave phenomena, right, even in +1 we have talked about the waves. So over there, right, when we talk about the wave phenomena, like for a propagating wave, this interference or superimposing, this is a fundamental difference between the wave phenomena and the particle theory. Like if you have say for example, you have here wave 1 and there is a wave 2. Now wave 1 we are keeping it as fixed. So this we are keeping it fixed to better visualize how the interference can be understood, and wave 2 pattern we are changing. Okay, so now you can see clearly in this visualization, right, what is it that we are able to observe. Like here, when the crust and crust are overlapping, right, what do you see? You will see that the resultant, this is what this is representing, how the resultant wave will actually exist. So you see here, when crust and crust are matching, right, you will see that amplitude will be maximum. But when crust and trough are matching, what do you see? They both will cancel. So when you have the wave coming from two sources, when they interfere or when they are superimposing, right, we will see that the resultant wave that we observe will be, we can think of it like what? It's like a addition of the two waves coming, like say for example here you represent the disturbance given by the wave 1 as y1, disturbance given by the wave 2 as what, y2. The overall disturbance is given by what, the addition of disturbance created by the wave 1 and disturbance created by the wave 2. But here when we go and study about the interference rate, we have already got some understanding from our +1. It is not like, we are going to add 1 + 2 like that. Here we have to consider what we call as the phase difference between the two waves. So when we are going to perform this superimposition, right, we have to consider what is the phase difference between these two waves that are undergoing the interference. We will study in detail about it, okay. But this is the fundamental difference between the wave theory and the particle theory, because as per the particle theory, right, if say for example there are some particles of light coming from one side and some particles of light coming from the other side, they would never be able to cancel. Like here what you see, if you consider the wave to be in the form of, light to be in the form of wave, right, you can see that there can be an addition where the amplitude is becoming maximum. So later we will see that that kind of an addition we will call it as what, the constructive interference. Same time we can also have a destructive interference where the waves will actually cancel each other, okay. So this kind of an pattern, right, can be observed only when we have anything exhibiting the wave properties. So we will see that scientists, they were able to prove that light in fact is able to demonstrate this interference phenomena, and hence that is the support for the wave theory of light, okay. But this is the fundamental difference between the wave concept of the light and the particle theory of light, okay. But we'll just start with how these things have developed over a period of time. So the first attempt to explain the observation with regard to the light is done by Descartes. So Descartes, maybe we might not be very much familiar with this name of the scientist, but we are definitely familiar with what he did. So he proposed what we popularly call as the corpuscular theory of light, okay. What is the corpuscular theory of light? It is nothing but the theory of light which proposes that light is consisting of very small size particles, and this corpuscular theory, right, is further expanded by the Newton, okay. So Isaac Newton, so his contribution is further expanded the corpuscular theory, and the corpuscular theory which considered that light is consisting of particles, and the size of these particles, right, will be different for different colored lights. So for yellow, the size of the particle will be different, for green colored, the size of the particle will be different, and so on, okay. And the corpuscular theory of light, again, so here the particles will be assumed to travel in straight lines, and this theory was able to explain the observation of reflection, refraction, though there are some problems associated with the way the corpuscular theory explains the refraction, okay. So corpuscular theory was not very successful in explaining why the speed of the light will decrease when you go into optically denser medium, because what we already have as an understanding is when we go from rarer medium to denser medium, what is going to happen? The denser medium will have a higher refractive index, and then speed of the light will be decreasing. But the theory wise, the corpuscular theory was not able to very comprehensively explain why the speed of the light will be decreasing when we move from a rarer medium to denser medium, but it was able to explain the phenomena of reflection and then refraction, okay. So this is about the corpuscular theory of light, which in the concept of Newton, he has coined this word called as what? Photons. The small particles of light, they are coined as what? Photons. And this theory, right, has got the blessing of one of the other giant in terms of the scientific world, that is Isaac Newton. So Isaac Newton, so in fact we have studied about it in the which chapter? In the modern physics, the photoelectric emission, photoelectric effect, okay. the explanation for the photoelectric emission or photoelectric effect, right, is provided by the Einstein's theory. And in that theory, right, he has considered that light is made up of what? Photons. Okay, so maybe you can just go back and check how the Einstein's theory for the photoelectric effect explains the observation by considering that light is made up of photons. Okay, the idea of threshold frequency, all of it can be explained only when we consider that light is made up of particles or photons. So this is on one side. So while people were agreeing to the idea that light is made up of particles, right, suddenly one kind of youngster has come and he challenged this idea. So he is Huygens, and it's a very interesting theory how even in the so-called scientific community, right, there can be this involvement of we don't want to call it by the word politics, but sort of a thing. The particle theory or the corpuscular theory of light is proposed or is involving some of the great names in the scientific community, whether it is Isaac Newton or the Einstein. And Huygens, he came up with the idea that light in fact has got a wave nature. Okay, so that is the theory that he has proposed. So Huygens proposed the wave nature of light. But the way he has proposed the wave nature, we will go and discuss about what is the Huygens theory of wave characteristics of light. But the way he has proposed the light, at the time people were not willing to accept it. Okay, for various reasons. I mean, of course, including the reason that the particle theory of light has got the blessings of some of the great people in the scientific community. But other than that, right, the Huygens theory of light as a wave, considering that the light will almost propagate like a mechanical wave. So the entire theory of the Huygens concept for explaining the wave nature of light is kind of based on the mechanical wave theory. So mechanical wave theory means what? Like you have a wave on a rope or ripples on water. All these are what? These are all the examples of the mechanical waves. Means mechanical waves will be requiring a medium. So at that time, right, the understanding of wave without a medium was not established. That came very late. Okay, so the moment we say a wave, people would tend to think that, you know, how is it possible that if you say that light is a wave, then light is able to travel through vacuum, because light is what will come from the star. Like in a solar system we have sun, so light will come from sun to earth, and in between there is a vacuum. So if you are proposing the wave nature for the light, how is it that light is able to travel from sun to the earth? So this is one of the fundamental questions that people are having. Okay, so that's one of the challenge for the people to accept the Huygens theory of light. And of course there are some drawbacks also. Okay, so the drawbacks and, you know, what are the details of the Huygens theory, we will try to cover up. But while initially people were not willing to accept the wave theory that is proposed by Huygens, Thomas Young, right, he came up with this experimental setup, so which is what we are going to study as the Young's double slit experiment, YDSC. So what he did is by passing the light through these two slits, he was able to establish the interference pattern. So Thomas Young, he was able to establish the interference pattern. So with this experiment, right, because the interference phenomena can be only performed by the wave nature. So after this experiment, people have to accept that, you know, light has got wave characteristics. But the initial theory that is proposed by Huygens, right, was having some drawbacks. So later, you know, the wave theory of light was further modified by Maxwell. So Maxwell, we talked about it in the electromagnetic wave chapter. So he has come up with the idea of the transverse electromagnetic wave theory. The oscillating electric field and magnetic field will maintain their directions perpendicular to the direction of propagation of wave. We talked about the Maxwell's theory of electromagnetic waves propagation. Okay, so Maxwell proposed the theory, and further the electromagnetic wave phenomena, right, is experimentally demonstrated by scientists like Hertz and other people. So the understanding of the wave theory of light, what began as an kind of a challenge to the greats of the science by youngster Heisen, with a very basic model of mostly considering the mechanical wave propagation concepts, that was supported by the Thomas Young's double slit experiment, which proves that light in fact will be able to demonstrate the interference. So even after Thomas Young, right, there were many scientists who have tried to demonstrate this interference and diffraction phenomena for the light. Okay, we are going to study about them in detail, but the wave theory of light suddenly took a different turn because of the Maxwell's contribution in terms of the electromagnetic wave theory. Okay, so the Heisen concept of the mechanical wave ideas, right, they were kept aside, and today when we talk about the light, we of course will have to accept that light has got a dual nature. Why? Because some experiments they demonstrate light to have the wave characteristics like this interference and diffraction, and some experiments like the photoelectric emission and Compton effect, they can be only explained. We talked about those two phenomena in the modern physics discussion. Those phenomena can be only explained when we consider the light is having the particle nature. Okay, so this is how the things have evolved over a period of time in terms of the understanding of the light. Okay, now what we'll do is we'll look at what are some of the highlights of the corpuscular theory and the Heisen's theory, and then we'll go into the details of the Heisen's theory. Okay, so the Newton's corpuscular theory, so it basically proposes that light consists of very small invisible elastic particles. They will be traveling in vacuum with a speed of light, which is 3 into 10 power 8 meter per second. And as we discussed, right, the size of these the corpuscular particles, right, for different colored lights it is going to be different. Okay, so for the yellow colored light it will have a different size, for the blue colored light it will have a different size, like that. So the theory was successful in explaining the basic phenomena like the reflection, refraction, etc. But this theory, why we are not able to completely accept the theory? Because it was not able to explain the interference. Means if we look at the interference phenomena, that can be only explained by the idea of the wave theory, correct? So the interference, diffraction, polarization, all these are what? All these are related to the wave theory. So these phenomena, right, could not be explained by the corpuscular theory of light. Okay, so this is about in brief on the Newton's corpuscular theory. Now looking at the other side, what we have is the Heisen's wave theory, right? Because in this chapter, right, we are not going to discuss too much into the electromagnetic wave theory, because electromagnetic wave theory we already have a separate chapter, right? Electromagnetic waves, we have discussed about it there. Okay, but here we are going to limit our focus to the Heisen's wave theory. So the Heisen's theory, right, it proposes that light basically propagates in the form of wave, and these waves, they will travel in all directions with the velocity of the light. Means if you have a source which we call as a point source, okay, like say even any object that is there, you can call it as a point source. So the light waves coming out of it, right, they will be able to travel in all the directions from that point source, and the different colored lights, they'll be having different wavelengths, because a wave will have what? Every wave will have a frequency and wavelength. So the difference is in terms of what? The different colored lights, they'll have a different wavelength. And the Heisen's theory also was able to explain the basic phenomena like the reflection part, refraction part. Other than those two, this theory was able to explain what? It was able to explain interference, diffraction, polarization. But where it fails in exactly those cases where the corpuscular theory is successful. What are the places where the corpuscular theory is successful? It is the photoelectric effect and the Compton's effect. So these two effects, maybe you can even again once check. We have discussed about these things in the modern physics chapters. Okay, so this is about the Huygens theory of light, and this theory, as we said, it broadly is based on the idea of light as a mechanical wave. Okay, so the Huygens theory is not about the idea of light as an electromagnetic wave, because that has happened much later through the Maxwell's proposition of the electromagnetic waves concept. But the Huygens theory is mostly based on considering the light to be a kind of a mechanical wave. Okay, and this theory, right, introduces the concept of what we call as the wavefront. So as we get into the details of the theory, we will be able to know what is this wavefront idea. But important things are what this theory is based on, almost giving a mechanical wave treatment for the light. And second thing is, this entire theory surrounds the idea of the wavefront. Okay, so first we will have to understand what is the wavefront, then we will go and learn about the Huygens wave theory. Okay, so in a propagating wave, right, like say for example, we have seen in +1 also we talked about the propagating wave. In a propagating wave, what happens, like think about it, you are dropping some stone into the water, you can see that there are ripples getting formed, and different points on the water will have a different level of disturbance. Okay, so different points on the water surface, they'll have different level of disturbance. Like if you can look at all the points which are having the same level of disturbance, so as the wave is propagating, we can create the surface, or whatever the shape you call it, where the points on that surface, right, will have the same level of disturbance. So we can say even they will have the same amplitude, like that. Okay, so what we can say, they will be having the same amplitude. Like typically if you look at the ripples on the surface of water, you see that the upward bump, right, that will keep propagating away from the point where you create disturbance. If you try to track that upward bump, right, at any point it will kind of form a circular boundary. So all the points on that circular boundary, right, we'll say what, they are having the same amplitude. So that boundary is what we will be calling as a wavefront. So what is the wavefront? It is nothing but locus. Like in mathematics we use the word locus, right? So what is the wavefront? It is the locus of points which oscillate in phase. Means if you look at a propagating wave, right, so what we will be having, like typically, I mean, we can write the equation like what, y is equal to a sine kx minus omega t, like that. Okay, the term inside this sine function is what we will be referring to as the phase, isn't it? That is the total phase. Whatever the term that is inside that sine function or cos function, whichever way we are writing the equation for the propagating wave, that entire term will be called as what? Phase. So when we see that all these particles are at the top of that upward bump, means they will be having the same displacement. Means the term inside the sine function should be same for all of them. So that is what we are essentially saying. So all the points on that wavefront will be oscillating in phase, means they will all have the same phase. Okay, so such a boundary is what we will be calling as a wavefront. Now the idea of wavefront, right, will be quite useful. Like even in electrostatics, right, when we try to look at the relation between what we call as an equipotential surface. In electrostatics also we will look at this, the relation between equipotential surface and the electric field. We can look at a similar kind of a relation here also. Okay, so we'll see what will be the relation. So like the way in electrostatics we have a relation between the equipotential surface and the electric field, right? So here we'll see how the wavefront concept will be able to help us in understanding better about the wave. So look at this, the speed with which the wavefront is moving, because so once you identify a wavefront, right, like say we are saying the locus of all the points which are having the upward bump, let us take it as a wavefront. Then the speed with which it is moving outwards from the source. So this is the source, right, where we create the disturbance. The speed with which it is moving away from the source, that will be nothing but what? The speed of the wave. The speed with which the wavefront is moving away from the source, that will be nothing but the speed of the wave. Okay. Not only that, if you want to understand in what direction the energy is propagating, okay, like I said, right, in case of this electrostatics, what do we have? If we have an point charge, the equipotential surface will be what? It will be like a spherical shell, and the electric field direction will be always perpendicular to the equipotential surface. The electric field direction will be always what? Perpendicular to the equipotential surface. Similarly, here also look at when you are able to create a wavefront, right? The direction in which the energy of the wave travels will be what? Always perpendicular. You can see how the energy will be propagating. It will be propagating. So we see our wavefront is what? Circular boundary. The energy will be propagating always perpendicular direction. Okay, so that is how we will be able to understand better about the wave when we are given information about the wavefront. Okay, now here you can tell, when we observe on the surface, right, of the water where we have created the ripple, what is the shape of the wavefront you are able to see? You are able to kind of see a circular boundary. So the shape of the wavefront is what? It is like a circular shape. Okay, now when we look at the wavefronts, right, in case of the source being the source which is producing light, generally we will be looking at three types of standard wavefronts. Okay, so that is what we will try to mostly cover. Okay, so we'll see the first one is what? If you have a point source, like S is a point source, then the point source will be able to create the light wave in all directions. So the wavefront, right, is going to be what? It is going to be a spherical wavefront. So here we are only seeing on one side of it, but the wavefront will be what? Spherical. On all directions it will be able to create the wavefront. And you can clearly see this is, a position of the wavefront at a time. After some time it is moving here, after some time it is moving here, like that. That is how the wavefront is actually moving. Now here S is the source, and the wavefront, if you look at AB as the wavefront is able to move. Already we have discussed about it. The speed with which the wavefront moves away from the source, that is nothing but the speed of the wave. In this case we are talking about the light wave. Okay, now if you look at the SP, SQ, SR, all these are what? They are representing the directions in which the light energy will propagate. You can see all of them are what? At any point you can see they will be perpendicular to the wavefront. So the direction of propagation of wave, that is also nothing but the direction in which the energy is propagating, right? Because the disturbance is the form of energy. So the direction of propagation of wave, or the direction in which energy travels, right, will be always perpendicular to the wavefront. So this is about a spherical wavefront. Okay, now when you look at any wave, we talk about the intensity of the wave. So even in +1 waves and oscillation chapter, we have looked at this relation between what is the intensity of the wave and its amplitude. So what is the relation? Intensity of a wave will be proportional to square of the amplitude. Intensity of the wave will be proportional to what? Square of the amplitude. What is the idea of intensity? If we consider a particular surface, then the power that is received per unit area. How do we define the intensity? Power received per unit area. Let's say the source power is P. What is the source power? P. If we look at a distance x from the source, on how much area this power will be incident, because spherical, right? Spherical means what will be surface area? 4 pi x square. That is the area on which the whatever the power of the source is incident. Now the intensity will be what? Power P divided by the area, 4 pi x square. So what we see here is intensity is proportional to 1 by x square. What we are able to see is intensity is proportional to what? 1 by x square. Already we know intensity is proportional to what? amplitude square. What is intensity is proportional to amplitude square. So if you just look at these two, right, the relation between amplitude and the position of the point from the source, what is it? If you take a relation between them, what do we have? Amplitude square is proportional to 1 by x square. We can say what? If you take a square root, means what we can say? The amplitude, right, will be proportional to 1 by x. So in case of a spherical wavefront, what is the relation between the amplitude of the wave with the position of the point or the position of the wavefront from the source? It is what? A is proportional to 1 by x. How are we able to get it? We are able to get it by using the intensity relation, because source will be producing the power, right? So whatever the power that is radiated by the source, that is what will be incident on a surface area at a distance. Based on that, we are able to understand what is the relation between the amplitude of the light wave with respect to the distance. So here you can see clearly what is it? As you move farther and farther, right, what is it that we are able to observe? Farther means the amplitude of that light wave, right, it is going to be what? Decreases, because what is the relation? A proportional to 1 by x. If you go farther from the source, means x value will be more, right? X is more means what? A will decrease. Okay, so this is about the spherical wavefront. The second type of wavefront is cylindrical wavefront. So when we will get a cylindrical wavefront, when you have the source of light linear, like you can think of a tube light. So the source of light is what? It's a linear. Okay, so it is going to create what we can call as a cylindrical wavefront. So what is it able to create? It will be able to create a cylindrical kind of, and so you can see that's the kind of a cylinder able to create, right? This is what? This is the wavefront. Okay, so if you have a linear source of light, like one of the easiest example that we can think of is what? The tube light. It will be able to sort of create a cylindrical wavefront. Okay, now again here also, whenever we talk about any particular type of wavefront, we will be interested in knowing how the amplitude of the wave produced will change with respect to distance. Say for example here, right, we are looking at a wavefront which is a distance x from the source. Okay, so if we consider the length of the cylinder to be L, then what is the total surface area on which the power produced by the, so this is source, right? Source will produce the power. The area on which the power produced by the source is incident is what? It will be the cylindrical area. What is cylindrical area? Pi. What is cylindrical area? 2 pi x into L. 2 pi RL, right? So here what is the radius? It is x. So cylindrical surface area is what? 2 pi RL. So it will be what? 2 pi x into L. Okay. Now when you look at the relation between intensity and amplitude, always the same relation, right? What is it? Intensity is proportional to square of the amplitude. So look at it. What do we have? What are we having? The intensity will be what? Power by area, right? Which is what? 2 pi xl, which means intensity is proportional to 1 by x. But intensity is what? Amplitude square. Intensity is amplitude square, which means if you look at these two, right, amplitude square is proportional to 1 by x. So from here what we can say? So if you take a square root, means what is it we can say? Amplitude is proportional to what? 1 by root x. If you take a square root, means what we can say? Amplitude proportional to what? 1 by root x. This is about the cylindrical wavefront. Okay, so again here also the relation is changing. Spherical means what we had? Amplitude is proportional to 1 by x. Cylindrical means amplitude proportional to 1 by root x. But here also same thing, right? As x is increasing means it is the denominator, root x is there in the denominator, right? X is increasing means amplitude value is going to decrease. Okay, so this is about the cylindrical wavefront. The third one, which is kind of a theoretical case, this will be what we'll call as a plane wavefront. So we'll see this assumption, right? Assumption of plane wavefront we will make when we are going to discuss about some of the phenomena, okay, with regard to the wave theory of the light. So when do we have a plane wavefront? Okay, so either you have a large sheet kind of a light source, okay, so that will be able to give you what? It will be able to give you the if you look at the wavefront, you will be able to have a plane wavefront. Otherwise, generally our sources are what? Point sources. If you have the light source which is very far off, means it is somewhere like in ray optics also we use that idea, right? When our source is at infinity or the object is at infinity, then the light rays coming from that, when they started, they would have started like what? Spherical wavefront. Because if you have a point object at infinity, they would have started like what? Spherical. But when you see very far, the spherical wavefront radius is going to be very, very large. Because what is the flat surface? Remember this idea we talked in the case of the ray optics also. What is the flat surface? Whose radius of curvature is infinity. What do you mean by flat surface? Whose radius of curvature is what? Infinity. If you have a wavefront that is starting from infinity, right? What will be the radius value starting from infinity? What will be the radius value? It is going to be very, very large, right? So when you have a point source which is very far off, then we can see that the wavefront, we can see it like what? It is like a plane wavefront. Now in case of the plane wavefront, right, one thing that we will be able to observe is that the intensity or the amplitude, they will be constant, because they are no longer going to vary with respect to the distance, because already we are very far from the source. So in case of the plane wavefront, whether we have, this is the ideal, we have like, you know, very large plane sheet kind of a light source. Otherwise we have a point source at infinity, and since the radius of that wavefront will be almost as close to infinity as possible, we can see like, you know, the wavefront will be almost like a flat surface for us. Okay, so that is how we will look at the assumption of the plane wavefront. And in this case, as we can see, the intensity or the amplitude, right, they are not going to be depending upon the position of the location from the source. So the amplitude as well as the intensity, they will be independent of the x value, because already we are very far off. So now with small distance changes, right, with small distance changes, we will not be able to observe much difference happening in terms of the intensity or the amplitude, because already we are at infinite distance from the source, right? So for small 1 centimeter, 2 centimeter like that, we are not going to observe any noticeable changes in terms of the intensity or the amplitude. Okay, so these are the three different types of wavefronts that we can think of when we are talking about the wave theory of the light. Okay, but we have to discuss about what is this Heisen's concept of wave nature for the light. So we'll see what are the things that he has proposed. So as we said, right, his idea is mostly based on the treatment of light like a mechanical wave. In fact, that is what people were initially agreeing to. So he has designed his entire theory based on the idea of light as a mechanical wave. So we'll see what it is. As per his theory, right, when there is a source, let's say we have a source at O. So here we are looking at what? We are looking at the point source. Okay, so we have a source. The source, we said, will produce a wave in all directions. Like you can see this F1, A, F2. This F1, A, F2, that is like a part of the spherical wave front. So what is this F1, A, F2? It is the part of the spherical wave front. So what is the wave front we are considering here? It is the spherical wave front. Okay. Now the Heisen's theory assumes that whenever you have a wave front, okay, now we are having a wave front. Okay. this wavefront, right, each and every point on the wavefront will act as a secondary source. So how he explains the propagation of the wave is, you are at some time you are having a wavefront. Okay, so this is F1, F2 is the wavefront. Now each and every point on this wavefront, right, will be acting as a secondary source. Okay, so each point of the wavefront is the source of secondary disturbance. Okay, and they are going to produce what we call as the wavelets. Okay, so the secondary disturbance is going to be called as what? Wavelets. You can see the point. So we are marking the points in the sky blue color here. Okay, so we are marking the points in the sky blue color. We can see there are 3 points that we marked. Okay, each of these points, okay, each of the point is going to produce the wavelets. Okay, and these wavelets, right, will be emanating, means they will be originating from that points on a wavefront, and they will be spreading out in all different directions. How they will spread out? They will be spreading out with the speed of the light. So understand this concept clearly. At a given time we have a wavefront. In this case it is what? A spherical wavefront. Now each and every point on that wavefront will create a secondary disturbance. So we call them as what? The wavelets. These wavelets will travel in all directions, and they will be traveling with what speed? Speed of light. Now the question is, how we will be able to see the wavefront at some time? Like once we have initially, let's say we are observing the F1, F2 as our wavefront. After some time, tau or t, whatever we represent, after some time tau, we want to know where this wavefront will actually exist. Like the way you can think of that upward bump on the surface of water. At some times you see that it is at a particular location. After some time, what will be the position of that upward bump? That's what we're trying to understand. We're trying to understand what is the position of the wavefront after some time tau. Now this is his concept. So this concept, right, is mostly based on geometrical construction. So how do we create the position of the wavefront at a time later? By using the idea of geometrical construction. So we'll see how he has proposed. So these wavelets, right, which are originating or emanating from the wavefront, we also generally refer them as what? Secondary wavelets. These are like the secondary sources. Okay, and you can see, so this is the S1, S2, S3. All these are the secondary wavelets. With what speed they will travel? They will travel at a speed which is equal to speed of light. Now if you mark the speed of light as v, let us say v is what? The speed of light. In time tau, these wavelets would have traveled how much distance? They would have traveled a distance of what? V into tau. Both in the forward. Forward means what? Anything away from the source is called as forward, as well as the backward. Okay, the secondary wavelets, because remember the point, what we are saying, the secondary disturbances, right, they will travel in all directions, means they will travel in forward as well as backward. So they will be covering a distance of what? V into tau. Now we can identify what is their position by using the geometrical construction. If we draw a common tangent to all these secondary wavelet spheres, because they will also be what? Spherical only, right? If you draw common tangent to all these secondary wavelet spheres, look at this. So we draw a common tangent. If we draw a common tangent to all these secondary wavelet spheres, like you can see on the forward direction side, if you draw a common tangent, means the tangent also, tangent need not be a straight line. The tangent here will be what? It will be a spherical surface here. So G A dash G2, that is the tangent that we can draw on the forward side. So the tangent, right, that we draw for all these secondary wavelets is what is going to represent the new position of the wavefront at a later point of time. Means after some time tau, you want to identify the position of the wavefront, means simply we will draw secondary wavelets. That's why we said it's what? Geometrical construction. Okay, so you draw secondary wavelets with a radius of how much, v into tau. You construct a tangential surface, which will be, in this case, what is it? It will be a spherical surface. It depends upon what is the kind of a source we are having. Okay, so if you connect all these tangents, right, we will get a surface here. That is what you are marking as G, A dash and G2. So this will represent the wave front. This will represent the wave front after a time tau. Now we'll have a question. What is it? We have only focused on the wavelets moving in the forward direction. But remember what we said in the discussion about the wavelets. What we said, the wavelets will be traveling in all directions, right? Means the way they will travel in the forward direction, they will also travel in the backward direction. The way they travel in the forward, they will also have to travel in the backward. But if they're traveling in the backward direction, right, then the concept of wave phenomena will be risked, because from the source, what do we see? That light will only be propagating in the forward direction, right? We will not see that no light is actually coming back again. If you go by this theory, right, the way there is a secondary wavelet moving forward, secondary wavelet also has to move in the backward direction. Means theoretically we should have a wavefront here also created. There is a D point, we can call it as A double dash, and D2. This D1, A double dash, D2, this also should represent wavefront. Okay, but we will see how Heisen has actually omitted the idea of the wavefront being formed in the backward direction. So we'll talk about, in fact, that is one of the drawbacks of the Heisen's theory. Okay, so he was not able to clearly give an explanation as to how he is able to omit. Okay, so we'll talk about it, but he has kind of omitted the idea of the secondary wavelets forming a wavefront on the backward direction also. That idea he has omitted. So we'll talk about it as we go into the discussion. So this is how we'll be able to create the position of the wavefront after some time in case of the point source. Now we can have it for the plane wavefront also. Like say for example, this is our F1, F2. This is our what? This is a plane wavefront. So we see a plane wavefront here at some time t, whatever we are observing. From there, we can say this is our starting time also. From there, if you want to understand what will be the position of the wavefront after some time tau. Okay, so after the time tau, we want to understand what will be the position of the wavefront. So again, what we are going to do, we will take all these points. Okay, because we are doing geometrical construction, right? We cannot take infinite points. We'll take countable number of points. A1, B1, C1, D1. From here we will create the secondary wavelets. What will be the radius of the secondary wavelets? V into tau. V is the speed of the light. Now you see the tangent that you draw for all the secondary wavelets, right? What is the tangent here? It is another plane. The tangent here is what? In the previous case, what we had? The previous case, the tangent is what? Like a spherical surface. In this case, the tangent is what? It will be like a planar surface. So this G1, G2, right? This G1, G2 is what? It represents the wavefront after time tau. Here also we can see from the point A1, we should have been having the secondary wavelets going in the opposite direction also, right? Isn't it? We should have been having the secondary wavelets going in the opposite, means they should be a wavefront which we can create in the backward direction also. But what Heisen proposed as a part of his postulates is that the amplitude of these secondary wavelets will be maximum in the forward direction. The secondary wavelets amplitude, right, will be maximum in the forward direction, and it will be zero in the backward direction. So this is where he was not able to clearly give an explanation. So when you say that each of these points on the wavefront can act as a secondary source, they will also be able to spread the wave in all different directions, right? In fact, that is what he also said. He said that wave will be spread in all different directions. But His another postulate is what? The wavelet's amplitude in the forward direction will be maximum, and in the backward direction the wavelet's amplitude is what? 0. So this postulate explanation, right, he was not able to provide successfully. So Eisen was not able to provide successfully as to why in the backward direction the amplitude of the secondary wavelet should actually be taken as 0. In fact, there were some later attempts by different other scientists who have come up with certain explanation as to how these secondary wavelets moving in the backward direction, their amplitudes will actually be almost becoming 0. So there are multiple attempts by different other scientists, but that is beyond our purview. Okay, so this is where we will have to limit our discussion about the Heisen's wave theory. Okay, so we see that it is based on the kind of treating the light wave like a mechanical wave. And what do we see here? We see that he has taken the idea of wavefront, the creation of the wavefront after some time by using the secondary wavelets. Okay, in that what is one drawback point? He has said that the forward direction movement of secondary wavelets, they will carry the maximum amplitude, backward direction they will have a 0 amplitude. That explanation he was not able to provide clearly. Okay, so this is about the Heisen's wave theory of light. And broadly, right, if you look at what are the achievements of the Heisen's theory. So Heisen's theory was able to, of course, explain the interference, diffraction, and polarization, all the wave phenomena, and it was also able to explain the reflection and refraction. In fact, in NCERT, right, you will be having the theoretical discussion as to how the Heisen's theory was able to explain the concept of reflection as well as the concept of refraction. So we will make a separate video about those. Here we are not going to go into the details of how Heisen's theory was able to explain the idea of reflection and refraction. Then the Heisen's theory has got some drawbacks. So what are the drawbacks of the Heisen's theory? One is it is based on the idea of treating the light as a mechanical wave using the concept of geometrical construction of wavefront. Okay, which completely got changed later. So once the Maxwell came up with the electromagnetic wave theory, all this is completely changed. And the other drawback is, in terms of his own theory, right, the propagation of disturbance through the secondary wavelets is limited to what? Only forward direction, based on one of his postulates. What he said, that forward direction the amplitude will be maximum, backward direction the amplitude will be what? 0. So that explanation also he was not able to provide, and that is the another drawback of the Heisen's theory. Okay, but so one of the successful thing about the Heisen's attempt is that he was able to challenge what is considered as pretty well established understanding of the light, which is the corpuscular theory of light, and with whatever the primitive understanding of the wave that was existing at that point of time, because the idea of the non-mechanical waves, or the waves which can travel in without a medium, like they can travel in vacuum, so that electromagnetic waves concept was not yet discovered. So he was still able to propose a theory to explain how light can exist as a wave, and using that concept he was able to provide explanation for all these wave phenomena associated with the light. Okay, so this is about the Heisen's wave theory of light, and in the next session, right, what we'll do is we'll start with a discussion about the concept of interference of waves. This is something that we have done again in +1 when we talk about the interference of the propagating waves. Again, here we will look at some of the results with regard to the interference of the waves, because at times, right, the only difference is there in +1 we will generally say wave. Here we will attach the word light. That's it. Okay. So we will go through the results in terms of the interference of the light waves, and then from there we will proceed to the experimental observations, the Young's double slit experiment, and so on. Okay. We will continue in the next class.